Yeah. Okay. So hello, everyone. So today's speaker is Jan Mikhail from the University of Copenhagen. So it's a great pleasure to have him here in the topology seminar. So he's going to tell us about the Abacus bicomodules, comodule configurations, and the Bour's equivalence. So please, Thomas, take it away.
Yes. Hello. Thank you for having me. It's a pleasure to be here with you. So the title is already on the screen, and I'll be talking about joint work with Joachim Kock, and this is available on the arXiv, with the arXiv number being spelled out here. So just a brief disclaimer: I'll be using the model-independent language for infinity categories consistently throughout. And I will even tend to skip the infinity prefix and just speak about categories. I also already prepared a little outline and the goals for this talk. So I will start with some preliminaries on two Segal spaces. Then I will explain the Bour's equivalence. And after that, I will describe our work, in which I will give some more general Bour's-like equivalences. And I will also show how it connects to Carlier's work on bicomodules. All right, and please feel free to interrupt at any time with questions. So, need to check the time. All right, so two Segal spaces. I will start with a reminder. A simplicial space is said to be Segal if the following squares in which we have the top face maps against bottom face maps. So these are asked to be pullbacks. For all n greater than or equal to 1. I also want to recall the definition of décalage. So let X be again a simplicial space. Explicitly, what this means is that we have a diagram of this shape here. Now, there are two ways in which we can extract another simplicial space out of this. First, we can delete x0. We delete all the simplicial operators to and from x0. And then we also delete all the top face maps. And this will give us what we call the top décalage. Alternatively, we can again delete x0 and the simplicial operators to and from x0, but this time we delete all the bottom face maps. And that will give us another, or it leaves us with another simplicial space, decbot of x.
Okay, Thomas, can I ask something quickly just to clarify?
Sure.
So when you say top and bottom, you mean in the first diagram, you mean dn plus 1 and d0, and then dn d0, right? Is that for the top? You mean
Right, this is the top face map and this is the bottom face map, which will be d0, and this one is d2.
Okay. Yeah.
Thanks. All right, so with these definitions, I can give a very compact definition of a two-Segal space. So a two-Segal space is a simplicial space if both the top décalage and the bottom décalage are Segal. All right. Remark. So two Segal spaces are the same thing as decomposition spaces. So two Segal spaces, these were discovered by Dikharov and Kaplanov. In the context of representation theory and Hall algebras, whereas decomposition spaces are due to Galvez, Kock, and Tonks. They are motivated by Möbius inversion and combinatorics. Particularly, the principal purpose of decomposition space is that it induces a co-algebra on which we can define Möbius inversion. Okay, so I will need one more gadget from decomposition space theory. And for that, I need a definition. So a map F of simplicial spaces is said to be Kulf if the following squares are pullbacks. For all except the top face maps and the bottom face maps. So
what is the notion here, you said?
And this is called Kulf.
Kulf, okay.
So the C stands for conservative and the ULF is for unique lifting factorization.
Thanks.
Sure. All right. I can now spell out the definition.
The phi, you mean F here, right? Or what is like F capital or phi? Like you mean? I think.
Sorry?
You mean the map F, right? F capital. You mean the map itself, right? Instead of phi.
Sorry, yes.
Or you mean okay. Or phi the map? Okay.
Yes, thank you.
You're welcome.
All right, I can now say what the bicomodule configuration is. The bicomodule configuration is a bisimplicial space of the following form. So first of all, we have the actual bisimplicial part. And I'll just do everything pictorially. Oops. Now, in addition to this, we also have an augmentation row up here, and we also have an augmentation column. So let me annotate everything. Here we have the augmentation row. That's a simplicial space Y. And here we have the augmentation column, which is a simplicial space X. And then these maps here are called the augmentation maps.
Is being recorded.
And I will refer to this as the.
I think Aziz, you have some background noise. Yeah, okay. Okay, sorry, since I unmuted myself, maybe I have a question. So Thomas, when you say simplicial space, do you mean simplicial set or do you allow these objects to be spaces?
I allow them to be spaces. Right,
No,
maybe I should have said that at the beginning. So I'm looking at functors into the infinity category of spaces, or the infinity category of infinity group organizations.
Okay, okay.
Yes. Thanks. All right, so the bicomodule configuration, this is the data, and this is required to satisfy certain axioms. First of all, we ask for x and y to be two Segal. We also ask for the augmentation maps to be Kulf. Next, we ask for the we ask for it to be double Segal. So this means that the rows and the columns in the bulk are Segal. And finally, we ask for it to be stable. So to explain what this means, let me introduce a convention. For the horizontal simplicial operators, I will use the letters D and S as usual. So here we have D top and D bottom. And for the vertical ones, I will use E and T. So here we have E bottom and E top. So stability means that all the squares of D top against E top are pullbacks, and all the squares D bottom against E bottom are also pullbacks. So just to motivate the word bicomodule, I already mentioned that decomposition spaces induce co-algebras. So here we have two, I meant to use the word two Segal spaces. So two Segal spaces induce co-algebras, and here we have two Segal spaces, x and y. And the remaining structure here is that's required in order to get a bicomodule over those two co-algebras induced by x and y. So that's where the name comes from. Now we'll skip the word configuration and just speak of bicomodules. All right. So now we can move on to the Bourse equivalence. So the starting point of the Bourse equivalence is the Waldhausen construction, which takes a stable infinity category and produces a simplicial space. I will not go into the details, but just as an example, if we have a stable infinity category C, then the three simplices of the Waldhausen construction will be sort of staircase diagrams of this shape. And here all the objects on the diagonal will be the zero object, and all of the squares are bi-pullbacks. There's pullbacks and push-out squares. So it turns out that the Waldhausen construction is actually a two Segal space. So this maps into this category. So this gives us the first example of two Segal spaces in this talk. Now the first observation of Bourse is that this factors through certain bisimplicial spaces. And we briefly describe this functor B. So Bij of a stable infinity category C, this is defined as the space of I, j grids in C, which are bi pullbacks. So for example, the 2, 3 space, this will be the space of all grids of this shape. which all squares are bipullbacks. So this will inherit certain properties from the axioms of the stable infinity category. So B of C will satisfy three properties. First of all, it is double Segal. It will be stable. In fact, that's where the name stable comes from. So we already see that there is some relation with the bicomodules of Carlier. And thirdly, it satisfies what we call the pointing axioms. So the pointing axiom says there exists a pointing map and this is just the space of zero objects in C. And it comes together with a map to the 0, 0 component, where this is just the core of C. So the map is just the inclusion of zero objects into all the objects. And this satisfies the following property, or I should say it endows the zeroth row with the structure, the local initial object structure. And I will explain what this is in a moment. And dually, it endows the zeroth column with the local terminal object structure. Let me say what the local initial object structure is. I will abbreviate this as Leo. So if X is a simplicial space, a local initial object structure is a pointing map like this, such that the following property holds. So first of all, consider the constant simplicial space on X minus 1. And this has a map to the constant simplicial space down to on X0. And this admits a map from bottom décalage of X, and we can consider the pullback of simplicial spaces. And there is also a canonical map from the décalage down to X given by the bottom face maps, and the condition says that this map here should be an equivalence. So let me give an example to motivate this definition. If X is Segal, and we have an object in X0, then we can form the pullback analogous to above. But this pullback will be precisely the co-slice category. And the projection of this map here down to X gives precisely the projection from the co-slice category down to X. And the condition that this is an equivalence says that X is an initial object. More generally, if we don't have a contractible space, then we will get local initial objects, that is, initial objects in each connected component of the category. So that's where the name comes from. All right. So we give some notation. So let's define sigma to be the co-cone on delta cross delta. So pictorially, we have the bisimplicial part, but we also have the pointing. And we can consider precies on that. And what we've seen is that B factors through precies on sigma. Let me introduce more notation. So I'll write this for the full subcategory, the precies category in sigma, satisfying the three conditions above, which I will call the Bose axioms. And then let me rewrite the triangle. What we have so far is this situation. The horizontal map here is obtained by right-hand extension from P, where P is defined by ordinal sum on I comma j, and it maps -1 to 0. So this is right-hand extension. And I can now state the theorem of Bose. The theorem is that this functor, is an equivalence. So the significance of this theorem is that the Waldhausen construction is not just an example, it's the example. Every two-figur space arises as the Waldhausen construction of a certain gadget, if only we interpret the Waldhausen construction in this more general sense. So we interpret this P lower star as a generalized Waldhausen construction. Moreover, the inverse P upper star is also a known functor with known years before. It's the total décalage. So what does the total décalage do? Given a simplicial space X, the total décalage is the bisimplicial space where we have the bottom deck as the first row, and we have the top deck as the first column, and we can fill it out appropriately. Whoops, sorry, I messed up the indices. And the pointing is given by x0. All right, let me see how I'm doing on time. Okay. So I can now move on to our work, starting with local initial object structures. So let X be a simplicial space with a local initial object structure. So this means there is a pullback condition satisfied, a pullback of simplicial spaces. On the degree 0, we have the following diagram. and I will call this map suggestively S-1. So here we have S-1. And then we formed this pullback. And here we have the bottom face map, and we asked for this to be an equivalence. So we may identify P with X0. Let me just record that. This is a pullback. So let me rewrite this yet again. So what we start with is this simplicial space. Together with the pointing. Now what the pullback gives us is, first of all, a face map from X0 to X-1. And it also gives us an extra bottom degeneracy here. And if we look at the entire pullback diagram as simplicial spaces, we actually get extra bottom degeneracies all the way up. What we conclude from here is that a Leo structure induces such a diagram. So I'll call the underlying diagram of this shape the simplex category sub B for bottom, extra bottom degeneracies, and altogether we get an element, a presheaf on that category. So what these maps do is, so this one, it just gives the connected component of X0, and this one picks out the 0 object, and this map here takes an object and maps it to the unique map from the 0 object to X. That's what the bottom degeneracy is. Okay, and this leads me to our first theorem. If we look at all delta B sheaves satisfying a certain property. So first of all these extra bottom degeneracies assemble into a map from X to the bottom decalage of X. And we ask this to be Cartesian. Then the category of these delta B diagrams is equivalent to the category of simplicial spaces with Leo structures. So the local initial object structures are equivalently described by these delta B diagrams satisfying this condition.
Thomas, I have a question. I think I missed the definition of delta B. So is it defined upstairs or is it?
I only said it quickly here. It's the underlying diagram of this shape here. So maybe I can quickly write it down here. So this diagram. So it's like the usual simplex category, but you have the additional -1 object.
Oh, it's just the augmentation of the simplex.
Yes, together with the extra bottom sections.
Okay.
Mm-hmm. Thanks. Mm-hmm. All right. Next, I want to describe the Abacus category. Fairly T. So this is the underlying shape category of bicomodule configurations. So again, I will only describe it pictorially. So first of all, we have the bulk part. Then we also have the augmentations. So the augmentation row up here. And the augmentation column. But in addition to this, we also have some diagonal maps. Which I'll generically denote by F, in which collectively called the Abacus maps. So pictorially, we can represent the I, j object as a column of beads, where we have I plus 1 black beads, and then we have j plus 1 white beads. So the horizontal simplicial operators, they act only on the white part. The vertical simplicial operators act only on the black part. And the Abacus maps, they preserve the number of beads, and they convert the bottom white bead into a black one. That's sort of where the name comes from. Think of it as like an abacus where you slide something from the left to the right. Okay, so there's one thing to note here. Using these abacus maps, we can compose it with the degeneracy, and that gives us an extra bottom degeneracy. And conversely, given those extra bottom degeneracies, we can compose it with this face map and recover the Abacus maps. So these are two equivalent descriptions of the Abacus category curly D. We can either describe curly D using the Abacus maps, or we can describe it with extra bottom sections or degeneracies in all rows except the augmentation row. Okay, now we're finally ready to start spelling out the equivalences. So the starting point is a functor Q from the simplex category times the walking arrow to curly D. Again, I will do this pictorially. So recall curly D has an augmentation column, it has an augmentation row, and it has a bulk. And it also has these Abacus maps. The domain of Q also has two copies of the simplex category, and it has a map between those. And the map Q simply maps these copies of the simplex category onto the augmentation row and the augmentation column, and the map between the two copies onto composites of the Abacus maps. So we can now consider the induced adjunction. where Q lower star is fully faithful. So our first goal is to describe the image. So if we start with a map of some different spaces in here, then the image is going to be a curly D diagram, something like this. And note first that if we look at the I+1th row, and that the Abacus maps, these will assemble into a simplicial map with codomain, the bottom decalage of the ith row. Let me record this here. So we have this simplicial map here. And the observation here is that this is Cartesian. And I'll call this the condition star. And this turns out to characterize the image of Q star. Proposition: a curly D diagram is in the image of Q lower star if star holds. So this gives us our first equivalence. So we started with this adjunction here. And we restrict it to an equivalence where we look at only those curly D diagrams which satisfy the star condition. Okay, I will later return to this diagram and I'll leave some space. Next, we want to put the Abacus bicomodule configuration axioms on the curly D diagram. And let Abacus bicomodule star be the full subcategory of those curly D presheaves satisfying the bicomodule configuration axioms. And the question is, what conditions do we have to put on the domain of Q lower star in order to make this an equivalence? And before I give that answer, I will give an intermediate definition just to motivate the final definition. So if X is a simplicial space, we say X is upper 2 Segal if the top decalage is Segal. So recall that this is half of the definition of a 2 Segal space. So there's also the dual notion of a lower 2 Segal space in which the bottom decalage is Segal, and if a simplicial space is both upper and lower 2 Segal, then it will be 2 Segal. But we are actually interested in a relative version of this. So let F be a simplicial map. We say this is relatively upper 2 Segal if the pullback is Segal. So here this pullback refers to this diagram. And this turns out to be precisely the notion which we need. So if we restrict here to the category here, where an object is a simplicial map with x and y being 2 Segal and f being relatively upper 2 Segal, then this functor restricts to an equivalence. So this is our next theorem. And finally, let me start with a lemma. If F is a simplicial map, then the image of F has invertible Abacus maps if and only if F is an equivalence. So by viewing two Segal spaces as the identity functor on a two Segal space, we get the category of two Segal spaces as a full subcategory. So we will just take the identity on a two Segal space, and then this equivalence restricts further down to equivalence with Abacus bicomodule configurations in which the Abacus maps are invertible. Yeah, I think I have 5 more minutes left. In these last 5 minutes, I want to explain the relation between sigma and curly D. So the starting point here is a functor J from sigma to curly D. We can describe this pictorially. So recall that sigma has a bisimplicial part, and it has this pointing here, and we map that onto curly D as follows. So curly D again has the bisimplicial part, and recall that curly D has the extra bottom sections. So this map here refers to the extra bottom section. To see how it fits into the remaining curly D, I'll use another color. So here, oops, here are the other extra bottom sections and the augmentation row and the augmentation column. So by restriction, we get a functor from curly D to sigma. Now, if we have a curly D pre-sheet and we look at its image, if B is double Segal, then so is the image. And if B is stable, then so is the image. This is rather straightforward. It's just because these conditions only refer to the bulk of the diagram. So they are just directly inherited. If now B is an Abacus bicomodule with invertible Abacus maps, then Q lower star, J upper star of B will also satisfy the pointing axioms. This is essentially because curly D already has the extra bottom sections, and by our first theorem, that gives us the local initial object structure on the row and the local terminal object structure on the zeros column. So altogether, A restricts to the functor. And the final theorem is that this is an equivalence. So let me fit that into our big diagram. So there's a functor J upper star here. And this restricts all the way down to this category. And this is an equivalence. Just quickly annotate everything. And as a final result, when we compose these two equivalences as a corollary, we can recover the original Bose equivalence. So indeed, this composite functor is precisely the tot functor. So we also get precisely the functors which appear in their equivalence. Okay, yeah, that completes my talk. Thank you very much.